ਬੱਚਿਓ, ਕੀ ਤੁਸੀਂ ਕਦੇ ਸੋਚਿਆ ਹੈ ਕਿ ਕਿਸੇ ਰਿਐਕਸ਼ਨ ਦੇ ਦੌਰਾਨ ਹੀਟ ਕਿਉਂ ਚੇਂਜ ਹੁੰਦੀ ਹੈ? ਅਸੀਂ ਜਾਣਦੇ ਹਾਂ ਕਿ ਐਂਡੋਥਰਮਿਕ ਰਿਐਕਸ਼ਨਸ ਵਿੱਚ ਹੀਟ ਐਬਜ਼ੌਰਬ ਹੁੰਦੀ ਹੈ, ਜਦੋਂ ਕਿ ਐਗਜ਼ੋਥਰਮਿਕ ਰਿਐਕਸ਼ਨਸ ਦੇ ਕੇਸ ਵਿੱਚ ਹੀਟ ਇਵੋਲਵ ਹੁੰਦੀ ਹੈ। ਵੈਲ, ਅੱਜ ਦੇ ਟੌਪਿਕ ਵਿੱਚ ਅਸੀਂ ਰਿਐਕਸ਼ਨਸ ਦੇ ਦੌਰਾਨ ਹੀਟ ਦੇ ਐਬਜ਼ੌਰਪਸ਼ਨ ਜਾਂ
ਇਵੋਲਿਊਸ਼ਨ
ਹੋਣ ਕਾਰਨ ਉਤਪੰਨ ਹੋਣ ਵਾਲੀਆਂ ਵੱਖਰੀਆਂ ਹੀਟ ਐਂਥੈਲਪੀਜ਼ ਬਾਰੇ ਗੱਲ ਕਰਾਂਗੇ। ਤੁਸੀਂ ਜਾਣ ਗਏ ਹੋ ਕਿ ਸਾਡਾ ਅੱਜ ਦਾ ਟੌਪਿਕ ਐਂਥੈਲਪੀਜ਼ ਆਫ ਰਿਐਕਸ਼ਨਸ ਹੈ। ਆਪਣੇ ਡਿਸਕਸ਼ਨ ਨੂੰ ਜਾਰੀ ਰੱਖਣ ਤੋਂ ਪਹਿਲਾਂ ਆਓ ਅੱਜ ਦੇ ਲਰਨਿੰਗ ਆਬਜੈਕਟਿਵਸ ਜਾਣ ਲਈਏ।
On completion of this topic, learners will be able to define various types of enthalpies of reactions, discuss enthalpies of reactions, solve numerical problems.
Students, to begin with our discussion on today's topic, let us take some examples of daily life to study exothermic and endothermic reactions. Making and melting of ice, condensation of rain from water vapor, evaporation of water. In all these chemical changes, heat is either absorbed or evolved when these reactions actually take place. एक exothermic process ਵਿੱਚ energy, heat, light ਜਾਂ sound ਦੀ form ਵਿੱਚ release ਹੁੰਦੀ ਹੈ। ਇਸ ਦੇ ਕਾਰਨ surroundings ਦਾ temperature ਵੀ ਵੱਧ ਜਾਂਦਾ ਹੈ। Exothermic reactions may occur spontaneously and result in higher randomness or entropy of the system, about which we will study in higher classes. Lab ਵਿੱਚ exothermic reactions heat produce ਕਰਦੇ ਹਨ ਜਾਂ explosive ਹੋ ਸਕਦੇ ਹਨ। Endothermic reactions ਵਿੱਚ energy absorb ਹੁੰਦੀ ਹੈ ਅਤੇ reaction ਦੇ ਦੌਰਾਨ temperature decrease ਹੁੰਦਾ ਹੈ। Endothermic reactions are characterized by positive heat flow into the reaction and thus an increase in enthalpy. ਅਸੀਂ ਇਸ ਨੂੰ ਇਉਂ ਵੀ ਕਹਿ ਸਕਦੇ ਹਾਂ ਕਿ endothermic process ਹੀਟ ਨੂੰ ਐਬਜ਼ੌਰਬ ਕਰ ਲੈਂਦਾ ਹੈ ਅਤੇ ਸਰਾਊਂਡਿੰਗਸ ਨੂੰ ਠੰਡਾ ਕਰ ਦਿੰਦਾ ਹੈ। Let us suppose in a chemical reaction, reactants combine to form products, and if H reactant denotes enthalpy of reactant, H product denotes enthalpy of product, and their difference is represented by delta H. We can say as delta H equals to enthalpy of product minus enthalpy of reactant. Delta H is equal to H product minus H reactant, or it can be written as change in enthalpy is equal to the difference of enthalpy of product and enthalpy of reactant. If delta H is positive, then it means that Hp is greater than Hr, thus heat is absorbed and the reaction is endothermic. If delta H is negative, then it means that Hp is lesser than Hr, thus heat is evolved and the reaction is exothermic. Standard enthalpy of reactions. Dear students, you know that heat of a reaction varies with temperature. The heat change that occurs when a process is carried out at 298 Kelvin and at 1 atmospheric pressure is called standard heat change. Or the standard enthalpy of reaction is the enthalpy change for a chemical reaction when all the participating substances are in their standard states. It is denoted as delta H0, where the superscript degree indicates the standard state. If the reactants and products are in their standard states, then the enthalpy of a reaction is termed as the standard enthalpy of reaction.
Let us calculate the standard enthalpy change for the shown chemical reaction. One molecule of gaseous sulfur dioxide reacts with two molecules of gaseous hydrogen sulfide to give three atoms of gaseous sulfur and two molecules of liquid water. Standard heat of formation of sulfur dioxide is minus 296.9 kilojoules per mole. Standard heat of formation of hydrogen sulfide is minus 20.15 kilojoules per mole. Standard heat of formation of water is minus 285.9 kilojoules per mole. Solution. Standard heat of formation of products is equal to 3 multiplied by standard heat of formation of sulfur plus 2 multiplied by standard heat of formation of water. On placing respective values, we get 3 into 0 plus 2 into minus 285.9 kilojoules, or minus 571.8 kilojoules. It shows that standard heat of formation of sulfur is equal to 0. Standard heat of formation of reactants is equal to the standard heat of formation of gaseous sulfur dioxide and 2 into standard heat of formation of gaseous hydrogen sulfide. On placing respective values, we get minus 296.9 plus 2 into minus 20.15 kilojoules, or is equal to minus 337.20 kilojoules. Standard heat of reaction is equal to standard heat of formation of products minus standard heat of formation of reactants. It is equal to minus 571.8 minus 337.20. It is also equal to minus 234.6 kilojoules.
Let us now discuss some different types of heats of reactions. Standard enthalpy of fusion. The standard enthalpy of fusion is the amount of thermal energy which must be absorbed or evolved for 1 mole of a substance to change states from a solid to a liquid or vice versa. It is also called the latent heat of fusion or the enthalpy change of fusion, and the temperature at which it occurs is called the melting point. Its symbol is shown as on the screen. Let us take an example of it. Solid ice changes to liquid water and the molar enthalpy of fusion of ice is plus 6.0 kilojoules per mole. Standard enthalpy of vaporization. The standard enthalpy of vaporization is the energy required to transform 1 mole of a liquid into a gas at constant temperature and under standard pressure. It is also known as the heat of vaporization or heat of evaporation. Its symbol is as shown on the screen. Let us take an example of it. liquid water changes to gaseous water and the molar enthalpy of vaporization of ice is plus 40.7 kilojoules per mole. Standard enthalpy of
sublimation.
Standard enthalpy of sublimation is the change in enthalpy when 1 mole of a solid substance sublimates at a constant temperature and under standard pressure at 1 bar. Its symbol is shown here. Let us take an example of it. Liquid iodine changes to gaseous iodine and the molar enthalpy of sublimation of iodine is plus 62.39 kilojoules per mole. Standard enthalpy of formation. The standard enthalpy change for the formation of 1 mole of a compound from its constituents present in elemental state is known as standard molar enthalpy of formation. Its symbol is shown on the screen. The heat change for the reaction shown on the screen is 92.2 kilojoules. Calculate the heat in formation of ammonia, and here is the solution. The heat of formation of ammonia is the heat change for the formation of 1 mole of ammonia from its elements, that is half molecule of gaseous nitrogen reacts with 3/2 molecules of gaseous hydrogen to form gaseous ammonia. Let us calculate the heat change for the reaction if delta H is equal to minus 92.2 kilojoules. This reaction corresponds to formation of 2 moles of ammonia. Thus, delta HF is equal to minus 92.2 upon 2, which is equal to minus 46.1 kilojoules per mole. Calculate enthalpy of formation of methane from the data shown on the screen. Solid carbon reacts with gaseous oxygen to form gaseous carbon dioxide. The enthalpy of formation in this process is minus 393.5 kilojoules per mole. This is equation number 1. Gaseous hydrogen reacts with half molecule of gaseous oxygen to form liquid water molecule. The enthalpy of formations in this process is minus 285.8 kilojoules per mole. This is equation number 2. Gaseous methane reacts with 2 molecules of gaseous oxygen to form gaseous carbon dioxide and 2 molecules of liquid water. The enthalpy of formation in this process is minus 890.3 kilojoules per mole. This is equation number 3. On multiplying equation 2 with 2 and adding to equation 1 and then subtracting equation 3 from the sum, we get solid carbon plus 2 molecules of gaseous hydrogen minus 1 molecule of gaseous methane is equal to 0, or heat of formation is equal to minus 393.5 plus 2 into minus 285.8 minus 890.3 is equal to minus 74.8 kilojoules per mole, or solid carbon plus 2 molecules of gaseous hydrogen form 1 molecule of gaseous methane. The enthalpy of formation in this process is minus 74.8 kilojoules per mole. Hence, the enthalpy of formation of methane is minus 74.8 kilojoules per mole. Standard enthalpy of combustion. The standard enthalpy of combustion is the amount of heat evolved when 1 mole of the substance under standard conditions is completely burnt to form the products also under standard conditions. It is denoted by the symbol shown on the screen. Calculate the enthalpy of combustion of ethylene gas to form carbon dioxide gas and water in gaseous state at 298 Kelvin and 1 atmosphere pressure. The enthalpies of formation of carbon dioxide, water and ethylene are minus 393.7, minus 241.8 and plus 52.3 kilojoules per mole respectively. Also determine the calorific value of ethylene gas. We aim that 1 mole of gaseous ethylene reacts with 3 moles of gaseous oxygen to form 2 moles of gaseous carbon dioxide and 2 moles of gaseous water. We are given enthalpies of formation of carbon dioxide, water and ethylene are minus 393.5, minus 241.8 and plus 52.3 kilojoules per mole. So, enthalpy of combustion is equal to the sum of enthalpies of products minus the sum of enthalpies of reactants. On placing the respective values, we get 2 into minus 393.5 plus 2 into minus 241.8 minus 52.3 plus 0. It is equal to minus 787 minus 483.6 minus 52.3. So, the final value of enthalpy of combustion is equal to minus 1322.9 kilojoules per mole. Before determining the value of calorific value, let us try to define calorific value. The calorific value of a fuel or food is the amount of heat in calories or joules produced from the complete combustion of 1 gram of the fuel or the food. Whereas heat or enthalpy of combustion is the amount of heat evolved when 1 mole of the substance is completely burnt. Thus, we can say that calorific value of a substance is equal to enthalpy of combustion upon gram molecular mass. Thus, calorific value of ethylene is equal to minus 1322.9 upon
28 is equal to minus 47.25 kilojoules per gram.
Let us take another type of heat, that is enthalpy of neutralization. The reaction in which an acid and a base react to give a salt and water is called neutralization reaction. Let us discuss about the nature of neutralization reactions. Neutralization reactions are exothermic in nature. It's time to discuss heat of neutralization. The heat change when 1 gram equivalent of an acid is completely neutralized by a base or vice versa in dilute solution is called heat of neutralization. Or we can say that the change in heat content or enthalpy of the system when 1 gram equivalent of an acid is neutralized by 1 gram equivalent of a base or vice versa in dilute solution. Examples of heat of neutralization are: let us look at a chemical reaction showing neutralization of hydrochloric acid with sodium hydroxide. Aqueous hydrochloric acid aqueous sodium hydroxide ਨਾਲ react ਕਰਕੇ aqueous sodium chloride ਅਤੇ liquid water ਬਣਾਉਂਦੇ ਹਨ। ਇਸ reaction ਵਿੱਚ minus 57.1 kilojoule per mole ਦੀ heat liberate ਹੁੰਦੀ ਹੈ। Or we can say that heat of neutralization in this chemical reaction is equal to minus 57.1 kilojoules per mole or minus 13.69 kilocalories per mole. Students, ਕੀ ਤੁਸੀਂ notice ਕੀਤਾ ਹੈ ਕਿ ਅਸੀਂ heat of neutralization ਦੀ definition ਵਿੱਚ ਇੱਕ term ग्राम इक्विवेलेंट ਨੂੰ ਯੂਜ਼ ਕੀਤਾ ਸੀ। ਇਸ ਦਾ ਕੀ ਮਤਲਬ ਹੁੰਦਾ ਹੈ? The reason is that neutralization reaction involves 1 mole of hydrogen ions and 1 mole of hydroxide ions to form 1 mole of water and 57.1 kilocalories of heat is liberated. Relevant chemical reaction ਤੁਸੀਂ screen ਤੇ ਵੇਖ ਸਕਦੇ ਹੋ। We can draw a conclusion on the basis of above discussion that the heat of neutralization of a strong acid and strong base is 13.7 kilocalories, no matter which acid or base is employed. But in case of neutralization of weak acid with strong base, the heat of neutralization is less than 57.1 kilojoules per mole. The value is also less in case of neutralization of strong acid with weak base. For example, let us first take the neutralization of weak base with strong acid. Aqueous hydrochloric acid reacts with aqueous ammonium hydroxide to form aqueous sodium chloride and liquid water. Minus 12.3 kilocalories heat is liberated in this reaction. So, heat of neutralization in this chemical reaction is equal to minus 12.3 kilocalories. आओ एक strong base ਅਤੇ weak acid ਦਾ example ਲੈਂਦੇ ਹਾਂ। Sodium hydroxide ਵਰਗਾ strong base completely ionize ਹੋ ਕੇ sodium ion ਅਤੇ hydroxide ion ਬਣਾਉਂਦਾ ਹੈ। Acetic acid ਜਿਹਾ weak acid ionize ਹੋ ਕੇ acetate ion ਅਤੇ hydrogen ion ਬਣਾਉਂਦਾ ਹੈ। ਇਸ process ਵਿੱਚ acetic acid ਦੀ dissociating ਵਿੱਚ 1.2 kilojoules heat energy use ਹੁੰਦੀ ਹੈ। The neutralization of acetic acid with sodium hydroxide takes place by the combination of hydroxide ion formed by the dissociation of aqueous sodium hydroxide and hydrogen ion formed by the dissociation of aqueous acetic acid. ਇਸ ਤਰ੍ਹਾਂ ਇਸ process ਵਿੱਚ minus 57.1 kilojoules heat energy produce ਹੁੰਦੀ ਹੈ। Thus, the overall liberated energy is less than 57.1 kilojoules, that is 55.9 kilojoules. Aqueous acetic acid reacts with aqueous sodium hydroxide to form sodium acetate and liquid water. In this process, heat produced is equal to minus 55.9 kilojoules. With the help of above examples, we can say that the neutralization process is not found only in the union of hydrogen and hydroxyl ions, but also the dissociation of the weak acid or base. On this basis, we can calculate the heat of dissociation of weak acid or base with the help of heat of neutralization. For example, the heat of dissociation of acetic acid is equal to 57.1 minus 55.9 is equal to 1.2 kilocalories per mole.
Numerical 1. 100 milliliters of 1 normal of an acid and 100 milliliters of 1 normal of a base are mixed at 298 Kelvin. During the experiment, the temperature arose to 298.0067 Kelvin. Calculate the heat of neutralization. Solution. Heat capacity of solution is equal to mass of solution into specific heat capacity. Total mass of solution is equal to 100 plus 100 is equal to 200 milliliters. Heat capacity of solution is equal to 200 into 4.2 is equal to 840 joules per Kelvin. Heat change in the reaction is equal to heat capacity multiplied by rise in temperature. It is equal to 840 joule per Kelvin multiplied by 298.0067 minus 298 Kelvin. It is equal to 840 multiplied by 0.0067 joules is equal to 5.63 joules. Now 1 gram equivalent of acid is equal to 1 normal hydrochloric acid in 1000 milliliters. 100 milliliters of 1 normal acid on neutralization gives heat is equal to 5.63 joules. 1000 milliliter of 1 normal acid on neutralization gives heat is equal to 5.63 upon 100 multiplied by 1000. It is equal to 56.3 joules. Heat of neutralization is equal to minus 56.3 joules. Numerical 2. Whenever an acid is neutralized by a base, the net reaction is written as shown here. Aqueous hydrogen ions react with aqueous hydroxide ions to form liquid water molecule and 57.1 kilojoules heat is released. Calculate the heat evolved for the following experiments. A. 0.60 moles of nitric acid solution is mixed with 0.30 moles of potassium hydroxide solution. Solution. According to the reaction, aqueous hydrogen ions react with aqueous hydroxide ions to form liquid water molecule and 57.1 kilojoule heat is released. When 1 mole of hydrogen ions and 1 mole of hydroxide ions are neutralized to form 1 mole of water, 57.1 kilojoule of energy is released. A. Heat evolved on mixing 0.60 mole of nitric acid with 0.30 mole of potassium hydroxide solution. Since nitric acid and potassium hydroxide are strong acids and bases, 0.60 mole of nitric acid is equivalent to 0.60 mole of hydrogen ions. 0.30 mole of potassium hydroxide is equivalent to 0.30 mole of hydroxide ions. In this case, out of 0.60 mole of hydrogen ions, only 0.30 mole will be neutralized by the base. 0.3 mole of hydrogen ions of nitric acid will remain unreacted. The net reaction is shown here. Now, heat evolved during the formation of 1 mole of water is equal to 57.1 kilojoules. Heat evolved in the formation of 0.3 mole of water is 57.1 multiplied by 0.3 is equal to 17.13 kilojoules.
Well students, now at the end of this topic, I hope you all have learned a lot in today's episode. Next time we will meet again to discuss another topic. Till then, goodbye.